Fusion Mobile, quality e-learning experience on the go.
Today we are handling electromagnetic field. Without wasting our time, I would immediately like to make a mathematical definition of electromagnetic field. In electromagnetic field, mathematically it is given as F equal to Q brackets E as a vector plus V as a vector cross B as a vector. E is electric field, V is velocity, and B is magnetic field. And resolving this, it's to bring a new equation which is F equal to BI, where I now is current, L sine theta. Force equal to BIL sine theta. Taking it from that point, we can now talk about applications of electromagnetism. First, we have the moving coil galvanometer, we have the electric motor. Then we can state advantages of moving coil galvanometer. The field produced by the horseshoe magnet and the soft iron core is very strong, as such external magnet field cannot influence it. That's one. 2. The instrument has a uniform space because of the radial field provided by the soft iron core. Remember, we are talking about the advantages of moving coil galvanometer. Moving coil galvanometer. It can be converted to read different ranges of current and potential differences by stably fitting appropriate resistances. These are the advantages. While the electric motor, we all know, if we consider in diagram, we have in the diagram a commutator, the carbon brush holder. There are two carbon brush round the commutator and the axis through which it turns. A number of coils of fine wire wound on a laminated soft iron armature. That is what it consists of. A set of brushes XY to allow current to enter and leave the windings. A commutator to reverse the current in the coils. Please, my dear, take that one very, very serious. They may ask you a question: what is the work of a commutator in the electric motor? The work is to reverse the current in the coils. Then it consists of external field coils also. So that's for electric motor. I've given you the equation down there. Then we can discuss the electromagnetic flux induction. Either moving the coil or source of flux relative to each other, or changing the magnitude of the source of flux in some way. This must create an induced EMF, as stated by Faraday. My friend do call him Friday, but it's not Friday, it's Faraday. Those days when we were in secondary school, SS1, SS2, if a teacher is dictating and call it Faraday, some of us think that is wrong, that it's supposed to be Friday. No, it's Faraday. Now let's move in for electromagnetic flux induction. Faraday's law of electromagnetic flux induction states that whenever there is a change in the magnetic flux linked with a circuit, an electromotive force E is induced, the strength of which is proportional to the rate of change of the flux linked with the circuit. While Lenz's law of electromagnetic induction states that the direction of the induced EMF is such that it tends to oppose the change that produces it. While Fleming's right hand rule, if the thumb and the first two fingers, I want you to practice that, my dear. Practice it as you read. If the thumb and the first two fingers of the right hand are held at right angles to each other, and the first finger is pointed in the direction of the magnetic field, and the thumb in the direction of the motion, the second finger gives the direction of the induced current. This will lead us to a wonderful topic known as simple alternating current circuits. But before then, please take a detailed study of electromagnetism so that you will have a sound understanding when we'll be discussing AC circuits.